Okay, so our last lecture, we basically were going through the various techniques that we can use for when we only have a single variable, single sample designs, and also when we have an independent variable, a predictor variable that's categorical with two levels. And again, if we only had a single variable, in other words, all we have is an outcome, all we have is a continuous dV, really the only thing we could do with that statistically is if we have a known previous population measure, we could use the t-test or z-test for independent samples. If we have two variables, we then ask, is one of those variables a categorical IV? And if so, how many levels does that IV have or conditions? And again, if the answer is it is a categorical IV with two levels, two conditions, we move to whether it's a between or within subjects. If it's a between within subject, a between design where different people are in each of those conditions, we have the t-test for independent measures. If it's a within subject design, we have the t-test for dependent measures. And again, within subjects means either highly matched methodologically, or they're the actual same people in each condition. They're exposed to both levels of your independent variable or your predictor. What we're going to look at today is what if your actual IV is continuous as well. So you have a continuous predictor, a single continuous predictor, and a single continuous outcome. And that takes us to either correlation or regression, and we're going to start with a review of correlation. So correlation. Correlation examines the relationship between two variables, and the assumption here is those variables are both continuous. So we have a continuous predictor and a continuous outcome, a continuous IV, a continuous DV. And continuous again means it's ratio data or it's interval data. In other words, you can make a relatively strong argument that each number does represent more or less of some construct and that the distance between each of those numbers is roughly the same. Now, there are three types of correlations, and it's the same statistical technique for the most part. There's a little bit of a difference in what we're doing behind the scenes, but each one's dependent on the type of variables we're using. The most common is the Pearson product moment coefficient correlation. Pretty long name, but that's the one that we use the most, and that is where both variables are continuous. So again, often it'll be shortened either a Pearson correlation, or if you just say you ran a correlation, most people know that's what you're implying. But the actual technical name is the Pearson's product moment coefficient correlation. There's also the point biserial correlation. And all this means is when you say you ran a point biserial correlation, you're letting the person know that you actually are using a dichotomous categorical IV or predictor. So generally speaking, normally you just run a t-test. So if you have a predictor or an IV that is categorical with two levels, dichotomous, and a continuous outcome, the appropriate statistical test, if all you were doing is a single test, would be a t-test, either between or within subjects. However, we're going to talk a lot about the fact that a lot of times we use correlations in a table, a correlation matrix, to simply examine all of the relationships that are going on in the data in a particular data set. It's often used as a descriptive overview at the start of a result section. So as a part of that, we might want to include some things like, for example, if we measured gender as a dichotomous variable, or if we included upperclassmen versus lowerclassmen as a dichotomous variable. Those might not be actual variables that we're interested in testing hypotheses on, but it might be interesting variables to basically just find out, are they related to anything else in your study? So anytime that you include an IV or predictor variable that is categorical at two levels, you can do a correlation with that. It is appropriate, but it's going to be called a point biserial correlation. And finally, there's the statistical adjustment that we can make to actually look at ordinal data. So it's a Spearman correlation. It can be used if we're looking at ordinal data, or we can use the Spearman's correlation with the conversions if, for example, we find that we can't seem to get around the assumptions of a regular correlation. In other words, a Pearson product moment coefficient correlation is a parametric statistic, which means it has assumptions. If the assumptions have been violated, one of our tools that we could still look at those violated assumptions with that data is to actually convert that data into a Spearman correlation and ran it, because the Spearman correlation does not have as many assumptions. It's also not as strong of a test. In other words, it's less likely to find effects. We'll talk a little bit about the Spearman correlation later in this lecture set. So just briefly, all correlations measure the association between two variables. They're looking for a relationship. As one goes up, does the other one go up? As one goes down, does the other one go down? Or as one goes up, does the other one go down, and vice versa? So we're not looking for causation. Remember, causation is done methodologically. We're simply looking for a mathematical relationship between variables. The value reflects the strength of the association, and that value of the correlation, the actual calculated value, ranges between 1.00 through 0 to negative 1.00. So if you get a correlation above 1.0 or below negative 1.0, you've done something wrong. It cannot happen mathematically. Now, the number, the absolute value, ignoring the positive or negative, is the strength of the relationship. So a negative 1.0 is just as strong as a positive 1.0. It's simply talking about the relationship and the nature of the relationship. So the sign reflects the direction. Negative is a negative correlation, which means as one variable goes up, the other one goes down. Positive is a positive correlation. As one variable goes up, the other one goes up as well. The actual test statistic is an italicized R. So R equals, and again, it will equal between negative 1.0 and positive 1.0. And it is independent of the scale of measurement. So a part of the process of calculating an R is to leave the original scale behind. Actually, effectively what's happening is a z-score transformation is a part of the calculation in such a way that R is always going to reflect 1 to negative 1, regardless of the scale of measurement. So just briefly, visually, correlations basically are often represented in scatter plots, and this would be an example of a fairly strong positive relationship. So again, on the horizontal and vertical axes are our two predictors, are our predictor and our outcome, our IV and our DV, the two variables that we think are related. And each dot represents someone's individual score on both of those. So this would be an example of a fairly strong positive relationship. And we usually will do what's called a line of best fit to represent our prediction based on that relationship. This would be a fairly strong negative relationship. As one variable is high, it's actually low on the other, and as that variable gets lower, the other variable gets high. So again, if we look at the far left top, that single dot at the top, far left top, represents someone that is very high on the vertical axis, but has a very low score on the horizontal axis. And likewise, if we go all the way to the bottom right, we see someone that is very high on the horizontal axis, but very low in their score on the vertical axis. This would be a negative relationship and also fairly strong. This would be an example of no relationship. There is no real pattern. What you scored on one variable really doesn't predict what you'd score on the other. There's no positive or negative relationship here, and that would usually be actually indicated by a flat line as far as our line of prediction or our line of best fit. Now be aware that if we get a zero correlation, if we find no relationship, that doesn't necessarily mean there's no relationship, because correlations make the assumption of linear relationships. So this would be an example of a scatter plot that if we ran a correlation on would indicate no relationship, but actually there's a fairly strong relationship. It's just the relationship changes as we move along the two variables. Initially, it's a positive relationship between our predictor and our outcome. However, at approximately a midpoint, it shifts into a negative relationship. And this is what we often refer to as an upside down U relationship. They're not super common in psychological studies, but they do occur. One of the best examples of it is actually what we know about arousal and performance. As you become more aroused, and by that I'm simply talking about physiological arousal, you're more alert, you're paying attention, you're a little nervous, your performance tends to get better. But at a certain point, that physiological arousal becomes a detriment. You become too nervous, too worried, you start second guessing yourself, and performance starts to go down. So truly decent performance, regardless of your skill level, is somewhere in the middle of your physiological arousal range. That would be an example of an upside down U. And in fact, it's kind of interesting historically that when scientists were originally looking at the nature of physiological arousal and performance in the late 1800s and early 1900s, the studies were all inconclusive because some of them found a positive relationship, some of them found no relationship, and some of them found a negative relationship. And effectively, almost research on the topic basically stopped. Scientists decided there really isn't a relationship here. We're just getting statistical random artifacts from various studies. It wasn't until a graduate student looked at all of these studies in combination and realized that the ones that found arousal in a positive relationship were usually looking at moderate arousal, and the relationships that were found in negative were usually looking at extreme arousal. He put together a study that looked at the entire range, and indeed what he found was the upside down U relationship that had been in plain sight the entire time, but constantly being somewhat missed by the fact that they were simply running linear correlations on their data. So a perfect correlation rarely exists in any kind of psychological research, but a perfect correlation would be that the line of best fit also represents in every individual score that you would find between the two variables. So for example, if there was a perfect correlation between weight and height, what we would find is that everyone's weight would perfectly predict their height and everyone's height would perfectly predict their weight. So the weight of A, the height of A would always fall in that line of best fit. And likewise, as weight increases, we'd expect height to increase. Now, a more likely situation is what we'd actually find if we correlate height and weight. And in that situation, we'd find that people that are 5'2" would vary in weight from a fairly low weight to a fairly medium weight, while people at 6'3", again, would probably vary from a medium weight to a fairly higher weight. And there would be some people that would actually be not necessarily well predicted. So someone at the top of the range of 5'2" might actually have the same weight as someone at the bottom of the range of 6'3". So this doesn't mean there isn't a relationship, but it means that the relationship is not a perfect relationship. In other words, knowing the relationship gives us the ability to make better guesses. So if, for example, if you told me you were 6'3", I would be able to tell from this data, I would probably guess, let's say that your weight was between 150 and 225. We're assuming that's the top and bottom of those yellow circles. And if you told me your height was 5'2", I'd probably predict, well, you're probably no more than 150 and maybe as low as 90, again, assuming that's what those magenta circles were representing. So that's more likely what we're going to find. And a lot of prediction in science, not just psychology, is based on correlations. In other words, they give us a better guess than just guessing. They give us some information to make a more informed decision, but not necessarily anything close to perfect prediction. Then again, if we actually scatter plotted this entire data set out, we'd probably see something like this, to where anywhere within this range, we've got a better guess. There is a relationship, but it's not perfect prediction. And again, the strength of the correlation tells us how good our prediction is. The stronger the R, the closer it gets to 1.0, the tighter that we're going to see that scatter plot cluster around our line of best fit or our line of prediction. So again, the stronger the correlation, the more we can predict with that relationship, and the more confident we can be of those predictions. As the correlations get weaker, the actual scatter plot gets more wide, and again, our predictions become less successful or less accurate. But even notice that this last one, the dark green circle, and our approximately 0.20, that's still a relationship. I still am better off knowing that data than not knowing anything. In other words, I can still make some decent predictions. If I know you scored very highly on one of the predictors, I've at least got a range. I'm no longer guessing, well, you could be anything on the other variable. I have a range, probably about 50% of that variable, but that's still better than not having any prediction. A lot of the predictions that we encounter every day are based on these kind of correlations. The relationship, and they're usually more complex correlations, but for example, the relationship of the various ways that we measure the weather give us prediction on what's going to happen. Now, it's not perfect prediction. It's why the weatherman often will say, or weather person will often say, there's a 32% chance of rain today. And that's basically what that's saying is that considering all of the current conditions on this day, other days that we saw these exact same conditions, 32% of the times on those days it rained. And if you actually looked at the success of meteorology, you'd actually find that it's remarkably accurate. that if they say there's a 30% chance of rain, we of course attend to the fact when it does rain and go, well, they were right, but if it doesn't rain, I thought they said it was going to rain today. They didn't say it was going to rain. They said there was a 30% chance of rain. And if we looked at every time they said there's a 30% chance of rain over multiple days, guess what we'd find? 30% of the time it rained. So again, that's an example of a science which has let us know about the error in its prediction fairly accurately and often gets maligned for it. So just recognize that there is value in prediction even if we don't have perfect prediction. It gives us the ability to make better decisions, especially better decisions than not having the data in the first place. And that's really the goal of correlations. Correlations, for the most part, are used to help us make decisions. Whether those decisions are about therapy, whether those decisions are about whether to hire someone or not, whether to let someone into graduate school or undergraduate, all of those are usually based on correlations. And again, the correlations are not perfect, but they let us make a more accurate decision than if we didn't use them. Now, I mentioned earlier correlation matrices. We'll often see these as descriptive terms that are used to kind of give people a big picture of our data before we start to get to our hypotheses and results sections. And the general idea here is that however many variables we have, there's a certain number of correlations we'll get from that. And if you want to kind of get just a quick guess, there's a quick equation here. You can take the number of variables, multiply it by the number of variables minus 1, and divide by 2. That will tell you the number of unique correlations you'd get out of that set of variables. So for example, in this case, the correlations, we see that we have 4 actual variables. We have hearing aid, hearing magnification, hearing new, and hearing perfect. And this is an actual data set from a study I did years ago. So there's 4 variables. So 4 minus 1 is 3. 3 times 4 is 12. 12 divided by 2 is 6. We're getting 6 unique correlations. And if you look at the table, you'll see that though there's more than 6 boxes, the diagonals are perfect correlations, 1.0, because they're the variable correlated with its own self. And then you'll see that the top quadrant of boxes, 6 boxes in a triangle, are the exact same numbers as the bottom quadrant of 6. Because again, we're just looking at the same correlation between the two variables, depending on whether we're looking at the first variable, for example, in hearing magnification going down the column, or hearing magnification going across the row. So a lot of times we won't actually present the data in both boxes. We may just present the bottom boxes and leave the top boxes empty because it's simply the same information. And again, this lets us just look at, broadly speaking, what are the relationships between all the variables we're looking about. And this isn't necessarily hypothesis driven, this is more descriptive. The degrees of freedom for correlations, by the way, are n-2. So let's talk briefly about the history of correlations, where they came from and who designed them. And that would be Karl Pearson, obviously, as he slapped his name on it, the Pearson product moment coefficient correlation. He was a British statistician born in 1857 and lived in 1936. He influenced Einstein. Karl Pearson wrote a book called The Grammar of Science, which really laid out the kind of systematic way that science should be done. And Einstein cited that book as one of his major sources in the way he looked at the world. He also was a contemporary of Gaston, who is pictured at the top at the far right, who was one of the founders of kind of measurement of personal differences, and also of Charles Darwin. So all of these were somewhat influenced or had influence on Karl Pearson, basically to say he was running with some of the greater minds of the time. Unfortunately, like a lot of statisticians, he also believed in eugenics. He believed that various groups of people, specifically noble Britishmen, were better than the rest of the world, and partly why he was creating statistics was to try to scientifically prove this. He did found Biometrica, and he was one of the co-founders of pretty much the still preeminent journal of statistical knowledge in our field. And he created the linear correlation, and he also was the one that penned the actual regression that we're going to talk about in a minute. Now, what's interesting about this is I already mentioned earlier in this lecture about how a graduate student figured out the upside down U relationship between performance and arousal by looking at past PhD and professors' research that hadn't quite put the picture together. Likewise, Karl Pearson is credited pretty much anywhere you read on creating the linear correlation and the regression, But again, about 20 years ago, a graduate student was poring through old English science journals, and he ran across an equation. And the equation was familiar because it was the correlation equation. However, it wasn't written by Carl Pearson. It was in an article by Francis Edgeworth. Now, Francis Edgeworth was an Irishman. He wasn't a eugenicist. He didn't run with all of the big names in science, but he actually published the mathematical equation for correlation in a journal years before Carl Pearson did. It really does look like either they came up with the same idea separately, but still Edgeworth got it in first, or Pearson was familiar with Edgeworth's work, had seen it, but also realized that he didn't have the clout to get it recognized and decided to repackage it as his own. We may never know, but I like to call the Pearson product moment coefficient, correlation coefficient, the Francis Edgeworth Pearson product moment coefficient correlation. Just as a little bit of an acknowledgement that it actually was created by Edgeworth.